Hi everyone, my name is Tianhao Zhang from UC Berkeley and Embodied Intelligence, and I'm going to briefly talk about this joint work with my colleagues and my advisor Pieter Abbeel. Our goal is learning deep visual policies for real-world manipulation tasks using practical amount of human efforts. To that end, imitation learning is a powerful paradigm which has led to many successes, but the successes are mainly in fields where collecting demonstrations suitable for learning is easy, such as autonomous driving. Unfortunately, this is not the case for learning visual policies for robotic manipulation. One can use kinesthetic teaching, but this is unintuitive, introduces visual artifacts, and doesn't guarantee that the demonstrator and the policy share the same observation space. You can also resort to trajectory optimization, but this often turns out to be time-consuming and challenging even for a robotic expert. Of course, there are existing teleoperation systems, but these systems are often expensive and specialized. To solve this challenge, we use virtual reality teleoperation to collect demonstrations. We were able to build such a system for a PR2 robot, where the demonstrator uses a VR headset to perceive the environment from robot onboard cameras and controls the robot with motion-tracked VR controllers. The resulting system is cheap, intuitive, unifies the observation space for humans and the robot, and introduces no visual artifacts. Here is our system in action, where I was controlling the robot in an intuitive and comfortable manner to provide demonstrations for a pick-and-place task. After we know how to collect high-quality demonstrations, the next question then becomes whether imitation learning can succeed. To that end, we propose a neural network architecture as shown in the figure, which takes color and depth images as well as end-effector positions as inputs and outputs the desired end-effector velocities. We used standard behavior cloning laws and auxiliary predictions to accelerate learning. We applied the single policy architecture mentioned earlier with the same hyperparameter settings to learn a range of manipulation tasks on a real PR2 robot. Our experimental results suggest that our approach that combines behavior cloning with high-quality demonstrations collected in VR is surprisingly effective. For each of the 10 tasks we consider, only less than 30 minutes of demonstration data is sufficient to learn a successful policy. Here we showcase how the learned policy performs for each of the 10 tasks. We invite you to visit our interactive poster session for more detailed discussion. Thank you for listening.